Me to this very nice conference with this very interesting audience and lots of nice talks. I'd like to apologize for being a little bit of an electronic salesman to begin with. I pulled a bait and switch on you and changed the title of my talk and what I'm going to say. And more than that, I'm actually going to talk about numerics, which makes me even feel more of like an electronic salesman. So these are two pictures, which I'll have more to say about in a minute. One, I think we've already seen twice in earlier talks, and the other, I hope, is a little bit new. So let me go on. So I'd like to begin, again, by thanking a few people. The first one on this list is Kaushik Balasubramanian, who came to me from MIT. He's a postdoc, and he did great things there, and he's beginning to do great things at Stony Brook as well. And also, I'd really like to thank Paul Chesler and Larry Yaffe, who let me look under the hood of their car, so to speak, let me look a little bit at their code, and even sent me some code, which was incredibly useful in what I'm about to show you. Okay, so I guess I can even do this. I'm telling you about the ABJM plasma. So we've already actually heard a lot about the ABJM plasma, except nobody used these words to describe it, right? It's this theory that was worked out by Aharoni, Bergman, Jeff Harris, and Maldacena. I think they were probably among the first to successfully explain what the field theory dual of this pure gravity in ADS4 really was. It's a rather, I guess, obscure from the point of view of most people in the audience, supersymmetric theory with lots of fields, non-abelian gauge groups, and so forth. We've learned over the years through the ADS-CFT correspondence that pure gravity in ADS4, in addition to describing this rather interesting theory from a string theory point of view, is also kind of a universal sector in this business of ADS-CFT. And so, I'm calling it exploring ABJM plasma, but really I'm exploring some universal sector in this ADS-CFT business. It's an example of a strongly interacting, relativistic, conformal fluid. What I'd like to do in today's talk is try and go a little bit beyond near equilibrium behavior. I'm not really there yet. It's been a long haul for me. I began working on this business, I think, back in February or so. I really wanted to talk about it. I think there was a nice conference in Trieste a few months ago, and I failed. And I wasn't even sure whether I'd be able to talk about it now. But, it's been 7 months, and it's time for me to open the books, I think, a little bit and show you what I'm up to. And, part of the point here is also to get some input from you. So please stop me and ask questions. So I want to know, going beyond near equilibrium behavior, what does turbulence look like? What do shock waves look like? When, if ever, is hydrodynamics no longer a good description of this kind of a material? We heard in Paul's talk and Louis Lehner that probably in a large class of examples, hydrodynamics describes this thing very well. What I'd really like to do, and I'm not going to be able to do it in today's talk, is probe the boundaries of this, see where hydro will begin to fail. All right, so some movies which seem to have become de rigueur at this meeting. So this movie you've seen, I think, twice before. So here it is the third time. This is the ABJM plasma. I started with the same initial conditions, I think, that Paul showed in his talk yesterday. Some sort of sinusoidal initial velocity profile, a counterflow, if you will. We can probably play it again. Oops. Play it again. So this is actually not a gravity code. This is just the relativistic hydrodynamics that Louis Lehner showed. So in some sense, it's completely equivalent to what he did. He showed us a few days ago. It's the ABJM plasma at second order in the gradient expansion. And what we're looking at is actually not the velocity profile, but the vorticity. So whether the fluid is flowing in some clockwise or counterclockwise orientation, and you see these small vortices joining to make bigger vortices, this inverse cascade that we heard about. So what I'd like to do is, again, sort of go beyond this. This was argued to be sort of pure hydrodynamics. is there some regime where we can go beyond this? And well, even in the class of pure hydrodynamics, there are lots of other examples we can begin to think about. Like there are other classic things we can do in hydrodynamics, like pipe flow or moving an object through the plasma. We can look at shock waves. We can look at the interplay between shock waves and turbulence. And so here's one simple, well, first I guess I can show you a slightly different movie. So yeah, I should say this movie I made with a lot of help from Paul's code. And this movie, I think is slightly better. It was made by Kaushik using Python code. So we have sort of a dual platform going at the moment. So I work in MATLAB. Kaushik works in Python. At the end of the day, we compare and see if it's similar. So one interesting thing, I guess, about this movie, you can see that the vorticity start to damp away over time. The vertical scale starts to decrease as time goes on. All right, so here's that other movie I wanted to show. So this is now hydrodynamics with sources. This is dragging a ball, if you will. It's again the ABJM plasma at second order and the gradient expansion. And what I was interested in looking at is a very simple kind of source, the simplest thing I could do. So instead of just having a flat metric on the boundary, you could imagine adding some dependence to the some spatial or time dependence to the time component of the metric. So this is sort of like varying the density in your fluid, making it maybe a little bit hotter or colder, a little bit less dense or more dense. And this is basically a cold ball or a bump in GTT in some non-Newtonian, in some Newtonian approximation. It's like introducing some small potential function, and we're going to move this ball up through the plasma. And you see a sort of classic structure here emerging. So this is periodic boundary conditions, so it looks kind of confusing. It looks very pretty, but it's also very confusing because the ripples come and wrap around the box. Let me show you a slightly cleaner movie on the next slide. So here's this cold ball again. And so what you see, it's moving faster than the speed of sound in this plasma. You see a shock wave forming in the front. You see a second shock wave forming in the back. And as the thing goes on, the shock waves begin to wrap around the box. That makes things a little bit complicated. But still, if you just focus on the central part of this movie, it's kind of a classic picture, classic example of a hydrodynamic experiment. This is a blunt object. Blunt objects have detached shocks in the front. And they have a secondary shock, which is usually attached in back. This is the temperature profile.
Is this gravity or
this is pure hydro. I'm not really going to be able to show you any gravity today. We're almost there. We're not quite there. So all this stuff is pure hydro. What I'd really like to do is be able to reproduce these two, this movie in gravity. So the movie I just showed, the movies of turbulence I just showed before, I think at this point we can do in gravity. On the one hand, that sounds very impressive. On the other hand, Paul gave me his code, so in some sense, all I needed to do was press start. The truth of it is something in between, which I'll explain as we go on. Are there any more questions about these movies? I thought I'd just get them out front, sort of the most colorful parts of my presentation, and after this, things get a bit drier. But this is the most easily accessible part. Yep.
Vorticity you're plotting here.
This is not the vorticity. This is temperature. This is temperature. Yeah. The vorticity is somehow less interesting here. I mean, that is something I'd like to. I mean, what you'd really like to see right here is some vortex train. Like maybe you could introduce some roughness to this ball, and you could watch vortices peeling off in the wake. That we can't really see very clearly yet. We don't have a good simulation of that.
What is the shock wave? Is it discontinuity in temperature or goes to infinity?
It's not. I say it's a shock wave, but we have dissipation. We have viscosities in here, and so the shock wave has some finite width. It's sort of in the inverse temperature. So we're not really beyond hydro in this picture.
So in the first two things you showed, the vortices, the Kaushik's thing looked much more sort of
sluggish? Is that
I think it just has to do with the frame rate.
okay?
I was fighting the frame rate yesterday. MATLAB may make slightly better movies, at least right off the bat, than Python.
Yeah, they're so very delicate. Like so, there has been enormous effort in, say, these people who built nuclear bombs, say, hydrogen codes and astrophysicists. In what regard is this different from that, enormous effort that has been raging since God knows 40s?
The short answer is I have no idea. It may be very similar. Yeah. I mean, I suspect they're not simulating the ABJM plasma, and I suspect they're not really interested in probing where this description will fail. But
Sure.
it may be very similar. Also, I think a lot of effort in hydro has been in incompressible Navier-Stokes, and this is relativistic and compressible, and so it's slightly different, and there's been less effort in that, I think.
Not so sure about his hydro codes when at Los Alamos, right?
Yeah. It's hard to know,
There's a
right?
book in it.
Any other questions before I go on? Okay. So let me tell you a little bit about where this stuff comes from. I'm going to be fairly vague, but I still want to give you a flavor. I can't call on my collaborator. Well, yeah. I can call on Larry, I guess, to give you a better description of the gravity side of things. But the hydro side, I'm going to tell you. I guess I just have to tell you. So the relativistic hydro code winds up being very straightforward to program. You're probably all familiar with this hydrodynamic expansion of the stress tensor, T mu nu. There's some ideal part, which depends on an energy density, a pressure, a force velocity, in this case a metric. I mean, often we just choose a Minkowski tensor if we're interested in flat space, but I really wanted to turn on these metric perturbations, so I've got to leave that in there. And then I have to leave room for first and second order dissipative terms, right? And that's all buried in this pi. So what's pi? Pi is this mess. There's a first order term which depends on viscosity, a shear viscosity. There's no bulk viscosity since I'm in a conformal plasma. Bulk viscosity would give me some non-zero trace for the stress tensor, and I don't want that, so there's no bulk viscosity, just the shear. And then I have a bunch of second order terms in general, which I copied from this nice paper by Bayer, Romaczki, Sun, and Starnets, and Stepanov. And it turns out in 2 dimensions, things get remarkably simple. I get to cross out a bunch of these terms. Well, for the particular metric perturbation I'm interested in, these curvature terms just aren't there. It turns out the product of these 2 pi functions, this particular product, and the product of these 2 vorticities also vanishes in 2 dimensions. So I'm left with a relatively simple structure. And I really need to keep some second order terms, I think especially this one, or my hydrocode will not be stable. Again, I'm interested in the conformal plasma, so this trace of this pi function must vanish. I also, I'm defining things here such that these first and second order terms are orthogonal to the force velocity, so that gives me another constraint. So if I count everything here, this began as a symmetric, I guess, 3x3 matrix, and I've gotten rid of a bunch of terms. I guess I start with, I get rid of a bunch of terms, and at the end of the day, so this is 3 constraints, 1 constraint is 4, so I start, I think, with 6, and at the end of the day, I only have 2 components of pi to worry about. That's not so bad. And then I can look up these coefficients, lambda 2 and tau pi, and also eta, which I think everyone at this point knows, this famous 1 over 4 pi times the entropy density. I can look these up in, for example, Ramstonk's nice paper from '08, although I think he wasn't the first to calculate these numbers, but it's a nice reference. So the numerical strategy is quite simple. You just take the temperature, the spatial velocities. The time component of the velocity is constrained because it's going to constrain the norm of this force velocity to be 1, and 2 components of pi. And this is a particularly nice choice, as Paul told me. Initially, I chose something different and had all kinds of problems, but choose these. Everything works out. And we'll just call these independent variables x. So I'm left essentially with 5 equations. The stress tensor conservation, that's 3, and then 2 equations defining these components pi xx minus yy and pi xy. So I basically have some sort of 5 by 5 matrix. I can write it out. dx dt is some complicated matrix polynomial in these variables x, and I just propagate using my favorite numerical scheme. And I suppose if you're good, you can do this quite rapidly. I think Romaczki was among the first to implement this second order hydro code for this, this particular plasma. It's not that hard. The gravity code, on the other hand, is quite a headache, and we're not quite there yet. We decided to do something a little bit different from what Paul and Larry were doing. I was reading this Living Review article by Winnicor about the characteristic formulation of gravity, and I was inspired by that. I really liked his metric, so I had my heart set on using this one, this particular form of the metric for my asymptotically ADS force space. And it's a bit different from what Paul and Larry did, which meant that even though Paul gave me his code, I had to rewrite some of the guts of it to adapt it for this particular choice. And so, so the form of the metric is somewhat different, but I think there's one very real difference between what we did. We make a very different gauge choice. So this is some Eddington-Finkelstein-like metric with this infalling radial coordinate z and a time coordinate tau. So in this characteristic formulation, what do? Right? You solve the equations on some slice of constant t. So that means you basically integrate a lot of equations in the radial direction z, and then after you do that, you propagate everything forward in t. So our difference, the difference between our code, they basically set beta equal to 0. So they wanted a nice simple coefficient for this ddz term in the metric. Whereas we, following Winnicor, decided we wanted to set the determinant of the spatial part of the metric. So that's where our code differs. More details are, of course, available on request. Are there any particular questions that you'd like to ask now about how this was done? I'll say a few more words about it, more on numerical schemes. So as pointed out by Winnicor, and also emphasized by Chesler and Yaffe, this metric ansatz allows for a nice nested solution scheme. So in hydro, remember, I had this 5 by 5 matrix that I kind of had to solve all at once and propagate forward in time. Here, one nice thing about this ansatz is that you only need really to propagate the spatial part of the metric HAB. So that's just 2 functions instead of, well, 5 in the hydro case right here, I guess naively something like 7 or 8. You also need to keep track of some boundary values, that's fine. But that's sort of 2 bulk fields and a couple of boundary fields instead of something like 8 in any given time step. And then the remaining fields are reconstructed time step by time step. So that allows for some, basically allows the code to run a bit faster than it would naively otherwise. I'll leave more details on this, since our scheme is really very similar to what Larry did. Larry and Paul did. I'll leave more details to Larry's talk tomorrow. So again, what we've done, we can more or less reproduce, I guess I've already said this, we can more or less reproduce what Adams, Chesler, and Liu did yesterday, I think. And we haven't done it yet, basically because I didn't want to run my computer for 2 weeks. But it was actually running when I left for this conference, and it seemed like it was going in the right direction. And also from the hydro point of view, we can reproduce this. And of course, on the gravity side, well, this is done without a metric source, right? This is propagating a state. So you choose some initial velocities, and you let the system relax to equilibrium in a flat metric. What we'd really like to be able to do is turn on some source for GTT, and I feel we're kind of almost there. At the moment, Kaushik and I seem to be having distinct problems with our code, which I think is very good news, because that probably means there's a bug rather than some real problem in the algorithm. So he's having problems with some code stability, and I'm having problems with some constraints, but I think my problem is a bug, and his problem is he's not filtering. So I think we're almost there. So far, we're only doing hydro, or what I'm going to talk to you about today is really only hydro. But in our regime, that's secretly pretty close to gravity. by this fluid gravity correspondence. And so optimistically, I can cite Hubini, Veronica, Mukund, and Shiraz Minwala, and tell you that I'm showing you these fluid gravity, I'm showing you these hydrodynamic solutions, but secretly in the regime I'm in, they're really also black hole solutions to a very high degree of accuracy. All right. So the movies are all very nice. What I'd like to do is extract some science from them in one way or another. So one, I think, interesting problem that we've certainly heard a lot about at this conference is translation breaking. How, for example, if we're interested in applying these systems to condensed matter, typically real-world materials do not have infinite DC conductivities unless they're superconductors. How do we get some reasonable model of a real-world material out of this? How do you get some finite DC conductivity? So many have focused on ionic lattices and scalar fields, and the list here is basically the speakers at this conference who I know have worked on this subject, and I apologize to those of you in the audience who've also worked on it, who I'm not citing, and any speakers I've forgotten, please tell me. But many have focused on these ionic lattices and scalar fields. So we can also, of course, because that's what I have at hand, that's the tool I have at hand, we could also, of course, consider some metric lattice, if you will, although I know Subir will probably object to that terminology since it's not really commensurate with some charge density, but I want to introduce some periodic metric perturbation and see what happens, given that's the tool I've developed so far. So there are many ways of getting at this answer. I think the quickest one from the point of view of giving a talk is this memory function formalism, because all I need to do is plug into a formula. If you're unhappy with this, let me just say that the result I'm about to give you can rederive just from the hydro equations if you feel like it. So this is described, I believe, in Forster's book on hydrodynamics, and it was introduced into this ADS-CFT correspondence a long time ago in this paper by Hartnell, Kofton, Muller, and Sachdev from 2007. And it's a way of calculating momentum relaxation, a way of figuring out how momentum relaxes or the system loses momentum over time, given some small breaking in the translation symmetry. And there are later uses in the ADS-CFT context, so I can shamelessly cite myself, and then there's this other paper by Hartnell and Hoffman, and probably other people I'm forgetting. But the idea is very simple. You take your favorite operator, and you couple it to some spatially dependent source, and you perturb your action. You assume this G, this is my perturbation, you assume this G is going to be small. And this memory method formalism will tell you that the relaxation time can be extracted from the imaginary part of the retarded Green's function for that particular operator. So, for example, if you're interested in these ionic lattices, that means you're sourcing some electric field, which couples, say, to a current. So you're calculating the imaginary part of some density or current correlation function, and that's giving you some relaxation time. Or maybe you want to break it with some scalar. That's also been done. So then you just consider the retarded Green's function for some scalar. Here, I've got a metric. So time component of the metric couples to the energy density. I'm going to be interested in the two-point function of the energy density.
So assumption of this formula is for G goes to 0?
Yes, this works. G goes to 0.
No, if G is irrelevant.
G is irrelevant. Relevant or irrelevant?
Irrelevant.
Irrelevant.
G has to be small in some appropriate sense.
But this works for the ordinary lattice system, which actually say suppose the physics are important at the lattice scale.
Well, I mean,
Omega goes to 0.
it's a perturbative calculation, right? I mean, the K is not perturbative. K you could make arbitrarily small in this formula.
Right. Yeah. I'm just wondering whether this, say, if you are interested in the physics at lattice scale, whether you can treat this as small perturbation or not.
I mean, that is energy, so that is momentum.
And that is momentum or energy.
You want to be at the chemical potential, or you want to be well below the chemical potential?
I want to near the. I want to be near to the boundary, say to the boundary of the Brownian zone. No.
Oh, good.
This is for systems where the effect of that lattice is a tiny perturbation.
No. It's for when it's irrelevant in the IR. So this is an homeostasis. This is about through the peak physics, which is long time physics. And it doesn't matter how strong the lattice is in the UV, as long as in late time physics it's small, you're done. So that's the answer.
Mm.
All right. So, stress tensor conservation with Joule heating. So I calculated some relaxation time. How does that plug in to some conductivity? Let me just remind you. So I have stress tensor conservation, and maybe I want to have some external field to drive my charge current. So here's my external field, here's my charge current. And what this relaxation time should do is it should modify this conservation equation by adding some term which is going to give me momentum relaxation. Okay, so the funny tensor structure is here to make sure that it's momentum that's relaxing and not energy, but it's not surprising, right? If I look at, say, the spatial component of this, that there'll be some 1 over tau here multiplying an energy current. So for small velocities, this thing gets much simpler. The left-hand side here is just some energy density times a time derivative of a velocity. The right-hand side, well, I get some relaxation time times that energy current. So an energy density times a velocity, that should give me an energy current. And then this piece here gives me an electric field times basically a charge density at leading order. And there's subleading terms here that I'm dropping, but I'm really only interested in the leading order effect here. And now I can deal with this, at least since I was a freshman in college. I want the steady state solution. I want the solution where the time derivative of v vanishes, and I want to know how the velocity and the electric field are related, or equivalently the velocity and the charge current, since the velocity and the charge current are going to be pinned here. And then comparing with Ohm's law, you just divide the electric field by the associated charge current, and you get this nice formula, which is almost familiar. If you want to go to the non-relativistic limit, maybe you should replace this n, which is a charge density, with, say, an electric charge times a number density. Maybe you want to replace this energy density with some mass times a number density. And then I think you can do the arithmetic in your head, and you'll see that standard form of Ohm's law coming out here. But important physics, at least in this hydrodynamic limit, is captured by this relaxation time. All right, so the metric lattice. My picture of what I'm doing is, and I'm sure people in the audience may object, but I found this a convenient cartoon, is to think of some shallow sea where I'm varying the height of, say, the bottom of the ocean. So I'm varying sort of the scale depth. And there are regions where it's shallower, regions where it's denser, and this is just a proxy for thinking about regions where the density is lower, where the density is higher. So here's my metric perturbation with a cosine. If GTT is greater than 1, I'm thinking of this as shallower, less density. So in a relativistic sense, the density scales with the temperature. That means colder temperatures. If GTT is less than 1, it looks deeper. So I've got more density or hotter temperatures. And the memory method, again, just tells us to consider the two-point function of this energy density. So the correlator has some universal form. My source for this was Pavel Kovtun's excellent lecture notes on hydrodynamics. I think there are many other sources at this point, but this one's nice because it's written in a notation that's fully relativistic. It doesn't require much translation on my part. So here it is, and you see this characteristic sound pole. Here's the speed of sound. There's some damping term, which has this nice characteristic form in terms of the shear viscosity. I've restored the bulk viscosity. I mean, it shouldn't be there in the conformal limit, but let's just put it back for kicks. And then there's some contact term there I don't really need to worry about. It's not going to contribute to the imaginary part. So I figure out the imaginary part. I take the zero frequency limit. I plug into my formula. There's some strange extra factors of 2 here, which come from the particular way the metric couples to the stress tensor and the fact that I'm using a cosine instead of an exponential function. And I have this nice form. Here's the entropy density showing up. And here's the speed of sound also showing up. So the speed of sound is kind of interesting that it shows up in this formula. It's telling you, I think, basically that this perturbation becomes very small in an incompressible limit. So this physics, if we're going to see physics come out of this, you're not going to see it in the Navier-Stokes, the incompressible limit of Navier-Stokes. This is something that's characteristic of a compressible fluid. Okay, so that's already a little bit maybe beyond what the ordinary run-of-the-mill stuff. And then we can further reduce this in the ADS-CFT case. Of course, in the ADS-CFT case, we can cross out the bulk viscosity. The shear viscosity, the entropy density ratio takes this universal value of 1/4 pi. And the speed of sound in this conformal case should be something like 1/2. So you can probably all do that in your head to get this nice relaxation time for this particular metric perturbation in this small k limit. So now, I mean, memory method function should be true for larger k, but I'm only computing here using hydro, so this is now only valid for both small g and small k. So what we've done, and this is maybe sort of a foregone conclusion, but it's nice to see our hydro code working. We've tried to look at this particular damping in our 2D hydro code. So we're going to introduce some sinusoidal perturbation in the metric. We're going to introduce some constant initial velocity profile in the direction of the bumps, and we're going to watch the velocity relax over time. And here's a plot of the log of the velocity, and we've rescaled the temperature using this relaxation time. And we see that for different values of the lattice, so different wavelengths of the perturbation, all of these curves kind of line up. So that's great. They all scale as k squared. And they're all roughly parallel to this line with slope 1, indicating that we've kind of got the right relaxation time there. And you can do this again for the size of the perturbation. You can look at different sizes of the metric perturbation. Again, they all kind of line up. They all scale as g squared, and they're all roughly parallel to that line of slope 1. So that's great. But then since this is a full hydro simulation, this is not just linear response, we get a little bit more here. One thing we can see is energy conservation. So there's a conserved energy, which you could work out from the hydro equations. It's something like an energy density times the velocity squared plus another form of the energy density. And this expression should be constant. And lo and behold, in our hydro simulation, it is roughly constant for different values of the lattice. But what does this mean? So if the velocity is decreasing, then of course something has to increase to keep this constant. What's going to increase is the temperature. So we can look at the temperature on the next plot. And here we have a simple nonlinear example of a conductor. You see the temperature increasing and asymptoting to some constant value. And again, all the curves kind of agree for different values of k and for different values of g. So we have temperature here on the y-axis and time rescaled in this particular way on the x-axis. So, Gary was talking about a very simple example of a nonlinear conductor in the first talk of this meeting, and I think this is arguably perhaps an even simpler one, since it's sort of pure hydro, and it's also secretly gravity through the ADS-CFT, through the fluid gravity correspondence. But it's nice to see. But this is all pure hydro, and so what I'd really like to do is go beyond this a little bit. So as already sort of emphasized, this memory method is valid at small g or relevant g, arbitrary k. And what can you say about large k? Well, from a WKB point of view, I think there are a number of indications in the literature that that relaxation time should go exponentially in k. I think this goes back to a paper by Sun and Starnets from 2002 and their subsequent calculations of various sorts. I haven't seen a calculation for the energy density itself. If someone knows of that, they should let me know. But roughly speaking, I think if we looked in this limit, if we were to compare, say, the gravity code, since the hydro code wouldn't be valid in this limit, compare the gravity code, with the memory method for large k, we should see some sort of exponential increase in the relaxation time. The hydro is valid at small k, but arbitrary b and g. And so there are other interesting areas to explore here. You can increase the velocity of the flow. And we have some preliminary indications for new kinds of behavior if your initial velocity is larger than the speed of sound. The relaxation time isn't just this logarithmic or exponential decrease. And also for large g, this g squared scaling gets renormalized, at least at the level of hydro, and you have some slightly more complicated expression. At least that's what the hydro seems to, the math seems to indicate, although we haven't really seen this in the code yet. And then again, for large k and g, which is really where we want to go to see where hydro breaks down, we'll need gravity. We aren't there quite yet. So I'm pretty much done. What's next beyond the lattice? We're also kind of interested in random metric perturbations and some model of impurities. We're interested in time-dependent metric perturbations and driven turbulence. Maybe if we have some time-dependent noise in this metric, we can really see this 5/3 Kolmogorov scaling. I don't know. And I'm also really interested in these moving shocks and shock waves and vortices and the role of roughness. I mean, if you introduce some bumpiness to your object, can you produce these vortices? Is there some transition to turbulence? And can you really see this roughness just at the level of hydro, or do you need gravity as sort of a microscopic model of what's going on? So with that, I think I'll end. I have a few slides later if people are interested about the sort of the corresponding calculation for the ionic lattices or the lattices in the electric field, but I'll leave that since my time seems to be up.
One of the things you mentioned as your motivation was to explore the sort of boundaries of hydro. I mean, one thing we know from first principles that it's an effective field theory with roughly zero radius convergence in momentum space. And from the black hole side, it's sort of clear why this is. Presence of higher quasi-normal modes which are neglected sort of tells you what the domain of the validity of hydro is. And the more so this recent work of Yannick and Heller and company, where they see the sort of higher quasi-normal modes by sort of doing a Borel summation. Is there something more than that you'd want to see in these simulations, or?
Well, I mean, so that's sort of a formal analysis of where hydro breaks down. I'm sort of interested in some physical processes where hydro would not be enough to explain the physics. So, and what I just showed you, I think, for example, incompressible hydro would not be enough to see this relaxation time. And if I were to increase the wave vector, decrease the wavelength of my perturbation, at some point, hydro itself is not going to be able to show me, not going to be able to account for this relaxation time either. And that's somehow a physical experiment. That you're interested in some conductivity. The conductivity you don't get purely from hydro in this model.
When you have these shock fronts, do you know what is sort of the structure, the detailed structure of the crest?
Of the crest and these shocks, we haven't really looked at it very carefully yet. We sort of mostly focused on getting the gravity code to work. And this feels like such a classic picture that there are probably many people at Los Alamos who've already done this lots of times. But
more Lockheed, airplane.
Yeah. But I suspect it looks, for example, very similar to, so there are these nice dragging string papers from Chesler and Yaffe from many years ago, and I think probably the shock there is similar to this shock, except there are two now instead of just one.
traditional hydrodynamics. If you go on the van, you will see the viscosity going logarithmically when you go to the infrared.
Yeah.
Did anybody investigate the effect of that on linear hydrodynamics or turbulence? Is there any effect one may expect?
I would guess there must be. I guess here I'm really sort of working strictly in the large N limit, and even in gravity I'm not really going to be able to see those effects, but they are interesting, yeah. And for real world physics, they're probably quite important.
Okay, that's the